to this video on growth and decay application problems. By the end of this video, you should be able to apply properties of exponential growth and decay to solve application problems. So let's take a look at our problems here. There's some vocabulary you have to know before we can start with this. You may or may not have had experience with some of these. A lot of it has to deal with finances. And the first thing you need to know is interest. Interest is money that is paid to account holder by a bank for allowing the bank to use their money. So when you deposit money in the bank, it doesn't just sit there and wait for you to come back. The bank uses that money to make more money for themselves, and they will pay you a little bit of money for that privilege. There's a couple kinds of interest we're going to talk about. There's simple interest, meaning it's being paid one time per year. They'll pay you money one time per year. Or compound interest. They'll pay you interest multiple times per year. And some key words to look for: appreciation, an object gains value after purchase. That means this is a growth problem. And depreciation, an object loses value after purchase. That's a decay problem. So you have to be able to identify our problems as growth or decay because it depends on which formula we use. Now, if we look at the growth and decay formulas for these application problems, you'll see they're identical except the growth has plus and the decay has minus. So they're the same thing. And then our compound interest has some extra stuff added in here, and so we'll talk about what all the letters mean. Okay, so in our problems, you'll see every one of them says A equals. A is just your final amount. What would we have at the end when I do all of this problems? Okay. The P stands for principal. Now, in finance, principal means the start amount. How much money did you put into the account? Or how many people were there initially? It's your initial amount. Okay. R stands for interest rate. Okay. And so what's important is when we're going to plug the interest rate into our equation, we have to take whatever the percentage is and divide it by 100 to take it out of percentage, because we don't want to put it in as a percent. And the last one, T, stands for time. Now, if you look at this, this is actually an exponential function, a times b to the x. This is our general form of our exponential function, but it's got using these different letters because we're talking about these word problems, so they have some different meanings. Okay, now in our compound interest, you see they have all the same letters, but they added the letter N, and N stands for the number of compounds per year. So how many times per year are they going to pay you interest? And that's what you'll plug into that spot. Okay. Keywords to help you understand what you're reading, whether it's growth, decay, or compound. So appreciate, increase, gains value, all of those are growth words. They're saying things are increasing as you go from left to right. Other words that they also have in here, doubles. That means inside the parentheses, right up here where it says 1 plus R, you would put a 2. 2 times, same thing. Where it says 1 plus R, you'll just write 2. It's already done the math for you. 3 times, and so forth. If they're telling you it's multiplying by this number, you just go ahead and input the number. You don't have to say 1 plus the number. It's already calculated out for you. For decay, important words are depreciate, decrease, loses value. That means it's getting smaller as it goes left to right. These last two, halves and quarters, it's similar to here. It's telling you what it's already multiplying by. So a half would be, you'd put 1/2 in the parenthesis. Quarters would be 1/4. So you don't have to say 1 minus a half. It's just a half. 1 minus 1/4, you just would put 1/4. It's already done the math for you. Now, for the number of compounds, they'll say the word compound is in the problem. That's the only time you're going to use this formula. So you're compounding n times yearly, and you'll plug in, well, what does that mean? So if I am being compounded yearly or annually, I'm getting paid interest 1 time per year, so that would just be 1. Quarterly means I'm getting paid 4 times per year, so I would plug 4 in for the n in the formula. Monthly, there's 12 months in 1 year. Weekly, there are 52 weeks in a year. And daily, banks use 365 days for the year. Okay, so let's take a look and try some of these out. So our first problem says, in 2000, the cost of tuition at a state university was $4,300. During the next 8 years, the tuition rose 4% each year. Write a model that gives the tuition Y in dollars T years after 2000. So a model is just the equation. Just write the equation without solving it. We're not solving anything, we're just writing the equation for it. So when I'm looking at this, I see 4,300. This is our initial value. That's our principal. That's how much it was at the beginning. And it says during the next 8 years. The next 8 years doesn't mean anything in this situation. It's talking about that's how the model was developed. But the tuition rose 4% each year. There's your interest rate, the percent. So you want to take the 4 and divide it by 100, and you'll get 0.04. That's what we're going to plug into our equation when we write it. Okay, so remember, here is our equation that we want to write. So let's plug in what we know. Now, the one thing they did say, write a model that gives the tuition Y. So instead of A, we would use Y because that's what it said, equals. Our initial amount was $4,300. This is a growth problem because it's rising, 1 plus, and then our R value is 0.04 to T. So this is the model for this. And a lot of times you'll see they'll go ahead and combine these two because they're like terms. So you'll see 1.04 to the T. Those say the same thing. All right, now how much would it cost to attend college in 2010? Well, this equation is built from 2000. So 10 years have passed from 2000 and 2010. So we're going to take our equation, and our time value here is 10 years. So we're going to plug in 10. Okay, when we put this into our calculator, you will get an answer of $6,365.05. Your calculator, money is 2 decimal places, so look in your calculator, look at 3 decimal places out and round the second one appropriately. Let's try it again. What would it cost to attend college in 2020? So it's $4,300 in 2000. We have a growth factor of 1.04. Well, 2000 to 2020 is 20 years. We'll plug in 20 there. And when we put that through our calculator, you get $9,421.83. All right, let's take a look at the back of this. All right, so let's take a look at this problem. So we have a 2015 Kia Optima. It depreciates, okay, so that word depreciate means decay. It depreciates at a rate of 12.6% per year, and the car was bought for $32,000. So a decay is your principal, 1 minus the interest rate raised to the time. Okay, so let's take a look. $32,000 is what the car was bought for, so that's your principal amount. Here's our interest rate. So if we take 12.6 and divide it by 100, we'll get 0.126. That's what we're going to plug into our equation. Now the one thing, this says 2011, just change that to 2015. It was a typo. So write a model that gives the value of the car Y in dollars T years after 2015. Okay, so they're not using A again. It's just a variable, so it doesn't really matter that much. But Y equals our principal amount, so $32,000. And this is a decay, so we say 1 minus. Well, we're minusing our interest rate right here, 0.126 raised to the T. So in the shortened version, that would be 32,000. 0.874 when I actually do 1 minus 0.126 raised to the T. Right? Now, how much is a car worth in 2018? So this is a 2015, it was worth $32,000. 2018 is 3 years later. So let's take our equation and plug in 3 for our time. And so after 3 years, the car was $32,000, and now it's worth $21,364.08. So it's dropped quite a bit. And we'll do it again for what it's worth right now. It's 2021. The car was bought in 2015, so that means 6 years. So $32,000.874 raised to the 6. And now, just 3 more years after the last time, this car is worth $14,263.25. All right, so hopefully you're picking up how to get this into your calculator. That's probably the hardest part of this, is making sure you get it input correctly. Now, our last set. You invest your $1,000 graduation money. So we've got $1,000 and we're going to invest it. The bank is offering 4% interest. Calculate how much money you have after 10 years if the bank compounds. Okay, so it says the word compounds. That means we're using this formula. 1 plus R, and that R gets divided by the number of compounds, and then the number of compounds times time. Okay, so let's check. Let's get our compounds. Quarterly, remember, was 4. Monthly compounds is 12. Weekly is 52. And daily is 365. Okay, so the $1,000, that's our initial value. So that's what we're depositing in our bank. 4% is our interest. Remember, it's 4 divided by 100, which makes the interest rate 0.04. Okay, and then each problem will be a little bit different because they're going to compound differently. So we have our $1,000, 1 plus, and that says R divided by N. Well, R was 0.04, our N was 4. Then I close the parenthesis and it says N times T. Well, N was 4, and T, oh, we didn't even mark that one. We should go back. Look, 10 years right here. That's our T value. So we're going to plug that in for each one. Now, I'm going to help you set these up. I want you to go back and try them to make sure you can input them into your calculator. So for monthly, compounding monthly, we have $1,000, 1 plus 0.04. But now we're compounding 12 times per year, so we put a 12 down here. And then it's 12 times 10 in your exponent. Okay. Weekly, everything starts the same, 1,000, 1 plus 0.04, but now we're going to get paid interest 52 times a year, and then it's 52 times 10 years. All right, and the last one, daily, 1,000, 1 plus 0.04. We're getting paid every single day, our interest, so we'll put 365 down there. And then it's N, which is 365 times T time. All right, go ahead and put these into your calculator. Let's see how you do. All right, so taking a look at these, I got 1488, 86, 1490, 83, 1491, 60, and 1491, 79. Now, it kind of, if you think about it, you might be expecting to get paid a whole lot more if you're getting paid interest more often, but you see, like, look, there's only 19 cents between these two. It really didn't make a big difference. There wasn't even $3 difference between the lowest one and the highest one. And the reason why is when they pay interest more often, they're paying interest on a smaller amount. And then you've got some division going on in your formula also. So the more times you're getting paid, you're getting a bigger divisor, which is making for a smaller number. Even though the exponent is big, it's still on a pretty small number. So it didn't make a big difference in the overall payout. All right. Hopefully that was helpful for you. Let me know if you have any questions. See you in class.